Flipped assignment on the rates of chemical reactions. So let me just kind of get things squared away here a little bit. Um, okay, so essentially, uh, the rate of something is never one number, it's always two numbers. It's the amount of change for a given amount of time. And the key with these chemical reactions is that we have to be able to physically, experimentally, on a large scale, record or see physically something changing. That's the key. Okay. Um, so it's over uh, the rate over time. Okay, so as an example, so if you look over here, it says calculate rate of reaction. If the reaction starts with no carbon dioxide, but after 50 seconds there exists some CO2. And again, there has to be something that has to record. We either have to see the gas evolving or some amount of gas going away. It could be a color change, could be a solid forming, but there has to be some change that we can see. Um, Typically, the way we write it is this delta right here just means change of concentration of something we can record over change in time. It's never one number, it's always two. Now, the next thing is, again, it always shows this, but you'll see these graphs a lot. Essentially, here at the very beginning of the reaction, we start off with a bunch of reactants and no products. Okay, and then essentially, as time goes on, the reactants are used up, the products are formed, and from this, if we can record one of those, again, we can record the rate. And we're actually hopefully going to be doing a lab with this as well that I hope to get done. Okay, so what has to happen for a reaction to occur? A couple of things have to happen. First of all, the molecules, whatever's going to react, has to be in the same space. It has to get close to each other. It has to have the right orientation. We usually have to break some bonds, like this one here, and then those bonds have to be in a situation that they reform to make the new products. All of those things, if we can affect those items, we can affect the rate of a reaction. Okay. Um, Basically, one of the things that they talk about, oppositely charged species tend to react more rapidly. We see this in um, uh, reactions where we took like copper sulfate and sodium carbonate. Ions with the same charge don't react. Bond strength plays a big deal on this as well. Now let's talk about the magnitude of the what we call the activation energy. Okay, the activation energy, and here's an example. Typically, it's wherever here's the potential energy of the reactants. We got to climb a little bit of hill to the activated complex, and then we get out the products. This from if you take the energy of the products minus the energy of the reactants, this is the energy of the total reaction. It doesn't include the activation energy. This right here, again, energy of the whole thing is just the products minus the reactants. This is an endothermic. We got to put in a lot more energy. Exothermic. We actually get out more energy. That being the case, and again, a really good way to see this. So here we can see, yeah, again, here's exothermic and here's endothermic. Now, a really good way to see this is definitely with an Adam Smith example. So we'll take a quick look at this one. And this is a really good idea because this can show the model. It can show everything happening all at once. I'm just going to sign here. We're just going to pick one real quick. Now, while we're waiting for this to pull up, there's talk about a catalyst. And a catalyst, what it does is that a catalyst actually lowers the activation energy without itself being changed. So if I go back into models, reaction lab, any one of these will show us, and we've seen this before in class. So here's a very exothermic reaction, but watch what happens. Again, this is a great example because you're given the diagram as well as the models. So we pull this along. Here's where the elements have a zero standard heat of formation. Here is the hydrogen to one oxygen. You can see we got to break bonds. Again, as we move this along, you got to get them close together. They have to be in the right orientation. We got to break the bonds. And as soon as those bonds reform, guess what happens? We get the products and they're going to go flying apart and we end up getting more energy out. And this shows, again, here's the activation energy, but the total energy for the reaction is we take whatever we have at the end and we subtract the beginning. Okay, so this would be the heat of formation of water. Okay, so meanwhile, back at this, so what are things that affect the rates of reactions? Okay, let's take a look at this one. As I noted before, presence of a catalyst. Catalyst itself does not change. It basically just lowers, it gives it a different pathway with a lower activation energy. It just gets to go there faster. And by the way, lots of money is involved in finding a good catalyst. And the nice thing about a catalyst, because it itself it does not change, we can use those over and over and over. So in industry, those things are worth a ton of money. Next thing is temperature. Okay, temperature as a general rule of thumb, hotter temperature, more odds that there'll be kinetic energy will be moving faster, greater odds that they're going to hit, which they have to react. That'll increase. As a general rule of thumb, every 10 degrees doubles the rate of a reaction, which means if you're in a fire, for instance, and it's getting hotter, you better get out in a hurry. Concentration, again, if we put more stuff in the barrel, in the pot, increase collisions, chances are it'll probably increase the rate. Most of this, I think, is pretty much common sense. And finally, here's really a summary of this. Structure of the species, the concentration of the species, temperature, we talked about that, presence of a gas. Now, if there are gases involved, this is really important. We can also affect it by increasing the pressure because we're forcing those things together. However, pressure has zero effect on liquids and solids, okay, or things that are aqueous. But pressure can definitely affect gases, and it makes sense. Higher pressure, the closer they are together, and that'll have a huge impact. And then this one is a classic example of something called the Haber process. This is a historical one. Germany, Franz Haber, World War One. They didn't have any gunpowder. He figured out a way to increase the rate of a reaction to actually pull nitrogen out of the air in lots of different ways. We'll talk about this with Le Chatelier's principle to make ammonia and therefore nitrates. And this process not only went on to make gunpowder, but it also went on to make fertilizer. And without this process, without trying to get these rates to go really fast and work well, we probably wouldn't have a chance of feeding 7 billion people on the planet. So this is kind of a key deal. So rates of reactions, we have to be able to see it, record it, whether something forming, something going away. The rate is affected by a catalyst, the nature of the particles, temperature, orientation, pressure if there's a gas, the number of collisions, and the concentration. That is basically, for the most part, rates of reactions 101. Thank you very much. Have an awesome day.